It's time to review the relative dating principles used to determine the proper geologic age order of rock sequences and structures to determine the timing of geologic events and eventually geologic histories. We will also cover the different types of unconformities as they represent the time gaps in geologic sequences. Shown here are MCC students trying to decipher the field relations from the top of the Redwall limestone near Skeleton Point in the Grand Canyon. Earth's history is recorded in its rocks, and a geologist is trained to interpret this history through the study of various rocks, fossils, structures, etc. In the 1780s, the Scottish geologist James Hutton promoted ideas on how to decipher the past in his scientific writing entitled Theory of the Earth. He is now recognized as having established geology as a science and is commonly referred to as the father of modern geology. In the 1830s, another Scottish geologist, Charles Lyell, popularized Hutton's work to the general public. With the publication of Principles of Geology, Lyell promoted the concept of Uniformitarianism. Uniformitarianism is a key principle in many scientific disciplines. And in geology, it can be summarized by the phrase, "The present is the key to the past." Simply put, this means that the same physical processes occurring today also operated in the past. So, if we study and understand our present physical environment, we may come to comprehend environments of the past as well. For example, observing processes related to the formation of these sand dunes today may help us understand ancient rocks formed from sand dunes. And if you think about it, the natural extension of this type of thinking yields the present is the key to the future. This is because processes occurring today also will occur in the future. They're governed by the same physical laws. So this will help us predict future events. The present is the key to the past, the present is the key to the future. It's a time kind of thing. But it's also a space kind of thing if you think about it as well. Processes occurring here on Earth are the same ones that are occurring on planets elsewhere in our galaxy and in the universe. In similar environments on other planets, streams are flowing, wind is blowing, the same physical processes are occurring there too. So, uniformitarianism is a simple but powerful concept. To decipher and reconstruct Earth's history, we need to be able to tell time. We can do this in one of two ways. The first is relative dating, where we can employ the same common sense observations used by Hutton and Lyell to place rocks and structures in a proper relative order. A second way is absolute dating, or isotopic dating, where lab analysis yields a specific age or number age that typically spans a range of thousands of years to millions of years to billions of years. For example, using relative dating methods, the ages of the rock layers in this canyon wall in the Grand Canyon can generally be described as older at the bottom and younger at the top. However, we don't know exactly how old or how young these layers are. That requires isotopic dating, which may or may not be possible. Let's go to Eremita Mesa real quick and look at the area we're talking about. This is just west of the South Rim Village at Grand Canyon. There's Hermit's Rest. That's the farthest you can go with a shuttle. The Hermit Trail goes down in the canyon there, and you can look west at Eremita Mesa. And there it is. The rocks at the bottom are older than the rocks at the top, but exactly how much older or younger we don't know. Let's talk about some basic principles used in relative dating. In 1669, the naturalist Nicholas Steno proposed several important relative dating principles in his Dissertationis Prodromus. And these are logical common sense ideas that one of my former professors jokingly referred to as the principles of duh. The first of Steno's relative dating principles is original horizontality, which he defined as strata either perpendicular to the horizon or inclined to the horizon were at any one time parallel to the horizon. Well, rephrasing, the principle of original horizontality simply states that some types of rock layers are originally deposited flat under the influence of gravity. This includes water-deposited sedimentary rocks, volcanic lava flows, and airfall tuffs that are commonly deposited on a level or near-level surface. This situation is displayed here by the relatively flat-lying mudstones of the Nonconformity Formation, exposed at the Vermilion Cliffs in northern Arizona. These are floodplain rocks, and so during times of flooding, streams can deposit tremendous amounts of mud on their bordering floodplains. And these are water-deposited sediments originally deposited in a flat or horizontal manner. Thus, an ancient river system, much like the one shown here at right, is likely responsible for depositing the muddy sediments, now sedimentary rock, of the Nonconformity Formation. Let's check out this location along the Vermilion Cliffs. And this is the Marble Canyon area near Lee's Ferry. There we are. There's where Highway 89A crosses. So these are the Vermilion Cliffs. And this reddish rock down here is the Nonconformity Formation. So relatively flat-lying mudstones that were originally deposited in a floodplain environment. But what if we see sedimentary or volcanic rock layers that are tilted, like these? Well, the simple interpretation is that if the layers are tilted, something must have happened since their deposition to tilt them. So, the simple interpretation is that these layers were originally horizontal in orientation, but have been disturbed since by some kind of tilting event. All we can really say about the timing of this tilting event is that it occurred after the layered rocks were laid down horizontally. This at least gives us a maximum age constraint on the timing of the tilting event. Conversely, if we see sedimentary or volcanic layers that are horizontal and not tilted, this likely means that these layers have not experienced any major tectonic events. Otherwise, the layers would be disturbed in some way. This evidence of absence can be important in dating plate tectonic events and mountain building events. For example, shown in this postage stamp, the mostly horizontal sedimentary layers near the bottom of the Grand Canyon are roughly 500 million years old. This would be the Tapete Sandstone, Bright Angel Shale, Muav Limestone. And so this suggests that the Grand Canyon has not experienced any significant tectonic deformation since these rocks were laid down 500 million years ago. The law of superposition states that in an upright sequence of sedimentary and volcanic rocks, the layers at the bottom are older than the layers at the top. So with certain rock types, the layers are sequentially deposited one on top of another on top of another. The term upright refers to rock layers that are flat or even tilted, just not overturned or flipped over. If the rock sequences are overturned, say by some kind of tectonic mountain building event, then superposition would not apply. Because in that case, the age sequence would be backwards, as you'd have younger rocks below older rocks. This scenario can occur, but is limited to certain geologic areas that have experienced significant tectonic deformation. The upper part of the Grand Canyon seen here from Yaqui Point looking west towards Mather Point includes flat-lying sedimentary rocks. And at the bottom here is the Redwall Limestone, the Supai Group, Hermit Formation, Coconino Sandstone, Toroweap Formation, and the Kaibab Formation on top. So superposition would tell us that the Redwall Limestone is older and the rocks get younger as you go up, with the Kaibab Formation being the youngest. Indeed, this section here is just part of the larger Grand Canyon section, so we're looking at the red wall here going up to the Kaibab, there are some rock layers farther down that are still relatively horizontal, and then we get into other rock units below. So if you were wondering, this is how Steno phrased his law of superposition. At the time when any given stratum was being formed, all the matter resting upon it was fluid, and therefore, at the time when the lower stratum was being formed, none of the upper strata existed. So again, the older rocks had to be there first, and then the younger rocks had to come in later. Let's go quickly to Mather Point and see this area firsthand. So here is the South Kaibab trailhead at Yaqui Point. And this is the view looking to the west towards Mather Point. In this view, this would be the red wall, the Supai, etc., all the way up to the Kaibab. Panning over this way, we can see the older rocks below the red wall, the Muav, Bright Angel, and Tapeats, and then the inner gorge. Cross-cutting relations is another simple yet powerful tool in our relative dating toolbox. And it says that geologic structures, like faults and intrusions, are younger than whatever they cross, offset, or bake. Here's an example of cross-cutting relations from a road cut at Resting Springs Pass near Death Valley, California. It's a student for scale, standing right in front of the volcanic tuff, this light-colored unit with the colored layers. And here's the fault. And obviously the fault is cutting through the tuff and offsetting the layers. So these age relations are easy to see and understand, but they can still only give us a relative sense of the age date of the fault. For example, all we really know about the fault is that it is younger than the volcanic tuff. Is it 10 years younger, 100 years, 1,000, million years? We really need more information. Now, if we had an isotopic age date on the volcanic tuff, say 20 million years, then we would at least be able to say that the fault is younger than 20 million years old. Here's another example, an intrusion cutting through some sedimentary rocks along Highway 93, just south of Hoover Dam. The sedimentary rocks were there, and in came the intrusion sometime later. The intrusion is younger than the sedimentary rocks. If you click on these globes, you can go to these places here near Death Valley National Park and here in northwestern Arizona. Again, in case you were wondering, this is how Steno phrased cross-cutting relations. If a body or discontinuity cuts across a stratum, it must have formed after the stratum. Makes sense. Lastly, we have the principle of inclusions, which was proposed by Charles Lyell. In essence, this principle states that a younger rock or host rock may contain pieces of older rocks, inclusions or clasts. Here's a geologic cross-section illustrating the principle of inclusions. We have an igneous intrusion here, this granite, surrounded by sedimentary rock around it and above it. There are inclusions of the sedimentary rock within the granite, and there are pebbles of the granite in the sedimentary rock here. With igneous rocks, like this granite intrusion, the inclusions of wall rock are often contained within the intrusion. The wall rock must have been there first, then the magma body intruded later and incorporated some of the wall rock within it. Thus, the wall rock inclusions are older than the host rock intrusion. So these inclusions are older than the granite intrusion. Here's an example. This lighter rock here is the host rock intrusion. So these inclusions are older than the host rock. With sedimentary rocks, inclusions or clasts commonly make up the larger rock type. So here we can see pebbles of granite, which are included within this larger rock unit here, say a conglomerate. So the pebbles are the inclusions or clasts. They must be older than the conglomerate itself. So the inclusions or clasts must be older than the host rock formation that contains them. Again, here's an example of rounded pebbles or clasts in a conglomerate unit, and so these rounded clasts must be older than the conglomerate itself. Fairly straightforward, simple, but powerful. This is a boulder that I happened upon during a hike in the Agua Fria River Gorge north of Phoenix, and it clearly displays a few relative dating principles, so let's look at it a little bit more closely. First, let's label a few of the different features. So we'll give them letters A, B, and C, and the first question will be, what two relative dating principles are displayed in this boulder? Yes, that's correct. Both the principle of cross-cutting relations and the principle of inclusions. We can see that feature B is cutting across both features C and A, so that's cross-cutting, and we can also see that the dark-colored A is an inclusion in unit C. Next, which lettered rock would be the oldest? Yes, correct again. It would be A. A is an inclusion in C, which means that it is older than C, and B cross-cuts C, so that it must be younger than C, and it also cross-cuts A as well, so it's younger than A, so A would be the oldest. Which lettered rock unit is then the youngest? Yeah, we kind of just answered that. Correct again. That would be B. B cross-cuts both C and A, so it's younger than both C and A. So, putting it all together, what is the correct relative order of features A, B, and C? So we just documented that A would be the oldest, followed by C, and lastly B is the youngest. So it's a simple exercise in applying the relative dating principles of cross-cutting relations and inclusions to figure out the relative order of units, in this case in a boulder. Okay, now we get to talk about unconformities, which are simply boundaries between older rocks and younger rocks that are significantly different in age. Specifically, an unconformity is a contact or boundary between adjacent rock units that represents a significant amount of geologic time, usually at least millions of years, and possibly billions of years. This image shows the famous outcrop at Siccar Point, Scotland, described by James Hutton in 1788. Note how the layered sedimentary rocks on the bottom are almost vertical in orientation, whereas the ones on the top are only gently tilted. The boundary between these two rocks is what we call an unconformity and represents a significant amount of geologic time. In this case, 55 million years. Now, Hutton didn't know the absolute age difference between these two units, but he did know that one was older and one was younger. And he surmised that the age gap was significant between the two. It had to be the amount of time between when the lower rocks were first deposited as sediment and then lithified, and then uplifted, tilted, folded, and eroded, all before the area subsided and the overlying unit was deposited as sediment, eventually to become a rock. So the gap had to represent not only a long time, but a geologically significant amount of time, usually meaning hundreds of thousands to millions of years, if not billions of years. For more about Siccar Point, just click on the book link there and it will describe the unconformity in Hutton's work. You can also click the Google Map link to take you to northern Scotland to visit the outcrop. And you can also see the last few slides in this presentation, which are dedicated to Siccar Point. There are three main types of unconformities: angular unconformities, nonconformities, and disconformities. Each is different depending on the rock type or the orientation of the rocks both above and below the boundary. Let's start with angular unconformities. This type of unconformity is a contact separating layers that have different orientations relative to each other, meaning that they are at different angles to each other above and below the unconformity. The layers are usually rocks that are laid down on the Earth's surface in a relatively horizontal way, like sedimentary beds or lava flows or ash tuffs. Here's an example of an angular unconformity in the eastern Grand Canyon, and you can see the beds in the bottom are relatively gently dipping off to the right, whereas the ones on the top are at a different orientation. So the boundary between the two is the angular unconformity. So typically the beds below the angular unconformity dip more steeply than the ones above. And this type of unconformity is very student-friendly in that it's very easily recognized, even from a distance. Let's visit this Eastern Grand Canyon angular unconformity. There's the Colorado River for reference. And if we back out just a little bit, we can see that the south rim is right here. And here's the entrance road and the South Rim Road and the Desert View overlook. Leighty Point, where the other image was taken, is right here. So you can see it's a long distance away. It's several miles away from the angular unconformity, yet it's really easy to see. So let's move across to the north side of the Colorado and zoom in and look at it, and we can see the angular unconformity. Of course, the Siccar Point example of an unconformity is the classic one, commonly known as Hutton's unconformity. And here we can see the steeply tilted sedimentary layers on the bottom, overlain by the more gently tilted ones on top, and there's the unconformity. Angular unconformities are formed over geologically significant amounts of time, and basically represent periods of tilting, folding, uplift, and erosion. So let's look at the sequence of events that happens in the making of one of these types of unconformities. This first panel represents the undisturbed deposition and lithification of sedimentary layers, one after another after another. Then comes a period of folding, tilting, and uplift, likely linked with some kind of tectonic event. Third, a period of erosion occurs both during and after the uplift. And then finally, a period of subsidence and deposition of new sedimentary material layered over top the tilted and folded layers below. So the angular unconformity simply represents the period of time from after the lower layers were formed until the upper layers were deposited on top. Nonconformities are another type of unconformity. This type of unconformity is a contact where sedimentary or volcanic rocks overlie older plutonic igneous or metamorphic rocks. Essentially, it's a boundary between rocks that form at depth, the plutonic igneous rocks or metamorphic rocks, and ones that form at the surface, the sedimentary or volcanic rocks. This type of unconformity is typically easy to see because of the different rock types involved, at least once you're able to recognize the difference between igneous, metamorphic, and sedimentary rocks. These images are of an unconformity exposed along the Colorado River in the Grand Canyon, and it separates rocks that are over 1 billion years different in age. It was termed the Great Unconformity by explorer John Wesley Powell in the 1860s. The Great Unconformity is widely exposed across the Grand Canyon, and let's look at one of these areas. This is the Stephen Isle area, located just to the west of the Grand Canyon Village Phantom Ranch area. If we zoom out and can see the eastern part of the Grand Canyon, the big bend of the Colorado River, and this is where Desert View is on the south rim. You can follow the rim road across to the Grand Canyon Village. Okay, here's the north rim, of course, and Stephen Isle is located a little bit to the west. This part of the Grand Canyon is dominated by mostly flat-lying Paleozoic sedimentary rocks, which have ages that range from about 500 million to about 270 million. However, at the river are some of the oldest rocks in the southwest, and they reach ages from 1750 million years old to as much as 1840. So if we zoom in on the Stephen Isle area, and we can see the Paleozoic layers here. Here are the sedimentary rocks. This is the lowest one, the Tapete Sandstone, which has an age of about 500 million years, and it's overlain by the Bright Angel Shale and eventually the Muav limestone above. And they're all Cambrian in age, or about 500 million or so. However, at the river are older rocks, and so these rocks right here are a sequence of older rocks of the Brahma schist, Vishnu schist, and Rama schist, and these have an age of about 1750. These are metamorphic rocks directly overlain by sedimentary rocks. So sedimentary over non-sedimentary, this is a nonconformity. And this nonconformity spans the range of over a billion years, as these rocks are 1750 in age and these are 500 million. That's 1200 million in change. This is the great unconformity that Powell described, where it's exposed in the Stephen Isle area. As with all unconformities, nonconformities are formed over a geologically significant length of time and represent a period of uplift and erosion. So let's look at the sequence of events that goes into making one of these unconformities. First, we have the undisturbed deposition and lithification of sedimentary layers, one after another. This is followed by a period of igneous intrusion by a magma into that sequence. And then third, a period of tilting, uplift, and erosion, likely linked to some kind of tectonic event. And then lastly, a period of subsidence and the deposition of new sedimentary layers over top of the older tilted layers below, and the intrusion. So the nonconformity represents the period of time from after the intrusion through all that tilting and uplift and erosion until when the upper layers were deposited on top. And we're left with a situation where rocks that are deposited at the Earth's surface, the sedimentary layers, are in direct contact with rocks that are formed deep within the Earth, the igneous rocks. A disconformity is the third type of unconformity, and these are contacts between adjacent but parallel younger and older sedimentary layers or volcanic layers. Disconformities are similar to an angular unconformity, except there's no angular difference between the layers above and below the unconformity. And like angular unconformities, disconformities are also formed over geologically significant lengths of time and represent periods of uplift and erosion. Since the layers are essentially parallel to each other, it's not thought that tilting is a major factor in the formation of a disconformity. The disconformity itself represents period of time from after when the lower layers were formed until when the upper layers were deposited on top. The rock layers above and below a disconformity are essentially parallel to each other and may even be the same rock type, making a disconformity relatively hard to recognize, even when you're standing right in front of it. It is only recognized by looking at other clues, like fossil sequences, inclusions, soil horizons, etc. This diagram at left shows two rock sequences with their various fossil assemblages. The one on the left is a continuous sequence of deposition where there is a progression of different fossil types from the lower layers to the upper layers. And the sequence on the right shows a sequence of fossils, but there's a missing section. By looking at the fossils, we can see that there's a number of different fossil types missing that are present in nearby sections. And so we surmise that there must be layers in there that had those fossils that have been eroded away. So by looking at the fossils and looking at their sequences, we can determine whether or not there are gaps in the sequence. The image at the right here is a cliff along the Bright Angel Trail in the Grand Canyon and includes two disconformities. All these are sedimentary rocks. All three units are millions of years different in age. The lowest unit there is the Muav limestone. It's Cambrian in age, over 500 million years old. The Temple Butte limestone is the one in the middle. That's even younger. And the upper unit is the Redwall limestone. That's Mississippian in age, roughly 350 million years in age. So there's millions of years difference between each one of these sedimentary layers. All three of them look very similar to each other. And the reason we know that there's a difference in time is really from looking at the fossils within each unit and some other clues. Let's look at where these disconformities are exposed along the Bright Angel Trail. So this is an area near Indian Gardens, which is along the trail below Grand Canyon Village. The trail winds its way down from the rim on its way to the river. The trailhead being up here. And so it makes its way down with these switchbacks through the steeper areas into the depths of the Grand Canyon. So here's Indian Gardens, and the trail will continue farther to the river eventually in Phantom Ranch. Here's the cliff sequence, with the Muav limestone being the lowest set of cliffs, the Temple Butte limestone, and then the Redwall limestone. And they're somewhat distorted here because the terrain is so steep. On the 3D view and maps, it distorts the image. This is a hypothetical geologic cross-section with many different rock units, and it displays several relative age dating relationships. The fill patterns of the rock units represent the type of rock, like the brick pattern is the sedimentary rock limestone. The dotted pattern represents the sedimentary rock sandstone, etc. We also refer to these kinds of cross-sections as sequence diagrams, as we are determining the sequence of relative ages of the units. Let's see if we can figure out this geologic puzzle now. First of all the layers are sedimentary except for F, D, and H, which are igneous. According to the law of superposition, in an upright sequence of sedimentary or volcanic rocks, the layers get younger from the bottom to the top. And the lower layers here are tilted, but still upright, as they haven't been overturned upside down. That means that Unit A is the oldest, and then Unit B and Unit C. But what's next? D or E? Well, D is an igneous intrusion called a sill, and it has inclusions of both C and E in it. The principle of inclusions tells us that the inclusions of C and E are older than the host rock D. So the sequence is thus A, B, C, E, then D, and then Unit F cuts through all of them. So using the principle of cross-cutting relations, we know that intrusion F must be next. So A, B, C, E, D, F. However, F does not cut through G, so it must be older than G. And then finally, superposition tells us that the remaining sequence goes G, H, I, J, and K. As a bonus question, between which two units did the tilting event occur? Yep, that's right. The tilting event occurred during the time between when Unit F intruded and when G was deposited horizontally over top. And we say that because F is basically tilted and G is not. So this is how we figure out the relative age sequence of different rock units and different geologic events using relative dating principles. These remaining slides include images provided by Dr. Edmund Stump from Arizona State University when he visited the Siccar Point locality in Scotland. Dr. Stump is now Professor Emeritus at ASU, and you can't miss him. He'll be the one in the orange shirt. So looking down the steep hill at the Hutton location at Siccar Point itself, there's the North Sea. Here's the unconformity with the steeply tilted rocks below and the more gently tilted rocks above. And so this is where you would start. And down on the outcrop here is the same view that Hutton had with the unconformity. And there's Dr. Stump. And he's standing just above the unconformity, what's known as Hutton's unconformity. This is the view along the coast, along the top of the unconformity. And these rocks here are the very coarse-grained layered rocks on top. Peeking out over here on the coastline are some of the vertical rocks that are below the unconformity. And here's a signboard which has lots of information about Siccar Point and its geology. Take a little time and read about the geologic events that formed Siccar Point and this unconformity. Well, that's all for now. Till next time.